Now this is our video on numbers. Now in this video what we are going to do is we are going to talk a bit about the basic kinds of numbers and how they came about. So numbers, they started with our need to count things, right? So I mean, to count things you need to have, let's say if I were to say that I got 5 apples, I need a representation for that number, and of course gradually it evolved into more complicated ways of expressing larger numbers, and we started using decimal and so on. So but initially the requirement for numbers came about with representation for simple numbers and so on, right? So 1 2 3 and so on, they all are called natural numbers. So natural numbers, right? However, with time, we needed to express the mathematical reality that I have nothing, right? So if I have no apples, uh, if I have no apple, then I needed a representation for none, which is 0, right? So natural numbers and 0 combined to become, they both combined to become whole numbers. So these are whole numbers, right? So you notice that natural numbers are a subset of whole numbers, right? Likewise, we needed to express the reality that there could be negative numbers. So if I gave you 5 apples, what is my mathematical reality? I'm short of 5 apples, which means there's -1, -2, and so on, all the way till negative infinity. All of these and all the whole numbers, they combine to become integers. Right? Now, after integers, there comes the need for expressing fractions. So I mean, using these numbers, we still can't express that I have just half an apple, right? So there came rational numbers, right? Rational numbers which were P over Q form, right? Where Q cannot be 0 in here, right? So these are all the rational numbers that I have. Now, now you notice that all the integers are a subset of rational numbers. Now the way this works, right, is once you have your P over Q in the minimized form, that means you've cancelled out all the common factors. If the denominator Q ends up being 1, then that number is going to fall inside this circle of integers. Otherwise, it is all going to be outside this circle, right? So the combination of denominator 1 and denominator not equal to 1, they are all the rational numbers that exist, right? However, with increasing sophistication, we came up with even more sophisticated computations like finding the under roots and all, right? So all of those numbers which cannot be expressed, under root 2, under root of 3 and so on, cube root of 5, all of these complicated numbers, they became irrational numbers, right? Now, the combination of rational and irrational, right? So the superset of both of these, excuse this line which is just crossed into rational, but actually this line should be covering the rational and the irrational completely. The combination of both of these is my real numbers. Okay, so this is this set combined real numbers. Now mind you, there's nothing outside of rational and irrational, okay, which is real. So it's basically the outer boundary of this and the outer boundary of this combines to give us the real numbers, right? So this is a very simple, almost simplistic representation of the different kinds of numbers that we're going to use. Now let's move on from here and let's talk about divisibility. Now, in terms of divisibility, now for some time now, I'm going to concentrate only on natural numbers, right? Because if you notice that if I got to divide something by a rational number, I'll always be able to divide that something. So it doesn't really make sense talking about divisibility by rational numbers. What I'm going to and division by 0 is anyway non-existent. So what we are going to do is we are going to talk about divisibility by natural numbers. Now 1 is a number which divides everything, right? So 1 is neither prime nor composite, so we'll not even talk about divisibility by 1. Divisibility by composite numbers can come in later, right? But let's talk, before we talk about divisibility and composite numbers and all, it's important to understand the prime numbers. Now prime numbers are those numbers which have exactly two factors, 1 and the number itself. So let's take the example 2, which is the smallest prime. Now the factors of 2 are 1 and 2 itself. Similarly, you look at 3. 3 is divisible only by 1 and itself. You look at 11. 11 is divisible by only 1 and itself. So all of these are prime numbers. Right? Now we've talked about the special status of 1. So 1 is neither prime nor composite. All the numbers which are not prime and which are not 1 are composite numbers, right? So all non-primes and non-1 numbers are composites. So by definition, you would have a composite number having at least 3 factors, right? We notice that prime have exactly 2 factors, 1 has exactly 1 factor, but composite numbers will have at least 3 factors. So apart from 1 and the number itself, we would find that there is at least 1 more factor. So I mean, just let's take an example, 6, let's say. So 6 is the factors of 6 are, so let me just start counting from the left hand side. 1 is a factor of 6 and 1 into something is 6, right? So I write 1 here and I write 6 here. So 1 into 6, this is the first factor pair of 6. Then the next is 2. Yes, it's divisible by 2. So 2 times 3 is the next factor pair of 6. Is there going to be another factor between 3 and 6? Absolutely no. So if I've started from this side and I'm going to cross over to the numbers I'm writing from the right hand side, as soon as I reach here, I'm done. That's it. That's all the factors of 6. So you notice that apart from 1 and 6, 6 has 2 other factors. So therefore this is a composite number. Now let's talk about divisibility. Now divisibility means, it simply means a number being divisible by another, right? So we'll start off by checking for divisibility by prime numbers. Okay, divisibility by prime numbers. Now in terms of prime numbers, we'll look at divisibility by 2 first. Okay, so let me take an example. Let me take a largest number, 472832, right? So if I go to test whether this number is divisible by 2 or not, what I simply do is I test whether this is an even number or not, which means I just look at this last digit. Now this last digit, if this is divisible by 2, then the entire number will be divisible by 2, right? But what's the logic? What's the logic behind just checking for this last digit? The logic is as follows. Let me rewrite the number 472832 as 472830 plus 2, right? Now if I've separated out this 2 here and the number 47283 has a 0 in the end, clearly this is a multiple of 10, right? And 10 is always a multiple of 2. So without even doing anything, all of these numbers with a 0 suffixed is a multiple of 2. So all I got to do is check whether this last digit is divisible by 2. So if something divisible by 2 is added to something which is divisible by 2, the sum will become divisible by 2, isn't it? So this is how, or rather this is why I just look at the last digit to verify whether a number is divisible by 2 or not. Yeah. Now let's look at divisibility by 4. Now let's look at the same number 4728 32. This time I separate out the last two digits, right? And using the same logic above, I separate out 32, right? Now to form this number, I actually need to write 472800 plus 32, right? Now just like this number was a multiple of 10 and therefore a multiple of 2, this number this time is a multiple of 100 and therefore a multiple of 4, right? So all I got to do is check whether this number is divisible by 4 or not, because a multiple of 4 plus a multiple of 4, the entire thing becomes a multiple of 4. A multiple of 4 plus a non-multiple of 4, the entire thing becomes not divisible by 4, right? So the logic here is pretty simple. Now you notice that 4 is 2 squared, right? So what we've really done is, when the power of 2 is 1 and I'm checking its divisibility, I look at just the one digit from the right hand side. If however the power of 2 is 2, then I'm checking for 2 digits. Now extending this logic, if let's say I were to check for 2 cube or 8, so the same number 472832, I this time separate out the last 3 digits, because 472832 is 472000 plus 832. Now this being a multiple of 1000 is actually 125 into 8. So this is already divisible by 8. Now if this is divisible by 8, then all I got to do is check whether this is divisible by 8 or not. So you notice that when the power of 2 is 3, and that's whose divisibility I'm checking, I just check for 3 digits. Now by this logic, isn't it simple to see that if I go to check the divisibility by 2 to the power 5 or 32, all I got to do is pick the check the number found by the last 5 digits, and that's it. You just need to check the last 5 digits, divide that number by 32, and if it divides, then that's it, the divisibility is done. Now can I extend the same logic to the powers of 5 also? Yes, I can. Why? Because when you look at this number 472832 and I separate out the last digit here, right, I get 472830. Now because this is a multiple of 10, it has to be a multiple of 5 also. Just like it was a multiple of 2, it has to be a multiple of 5 also. So if let's say I take 472875, and if I go to test whether this is divisible by 5 or not, right, divisibility by 5, what I do is I separate 472870 and 5. Now this has to be divisible by 5. Now if this is divisible by 5, then the sum is already divisible by 5. Likewise, just like I did for 4, 5 squared or 25, I separate out 472800 plus 75. So this time I picked last 2 digits here, because there is 2 zeros here, it's a multiple of 100 and therefore it's a multiple of 25. So if 75 is divisible by 25, the whole number will be divisible by 25. And likewise, so for 5 cube, all I got to do is test 875 and no more. Worry about it no more, right? So this is how we check for divisibility by powers of 2 and powers of 5.